We're going to talk about section 6.1, slope fields and Euler's method. Slope fields is a review of an AB topic, but Euler's method is a new thing that's in BC Calc, that's on the BC syllabus. So first, a lot of kind of clarification of vocabulary. An equation involving a derivative is known as a differential equation, which is commonly abbreviated as a DE. Sometimes you may hear it as an ODE, an ordinary differential equation. The order of a differential equation is the highest derivative involved. So for example, y double prime plus 2y prime equals x is a second order differential equation because there's a second derivative in there. dy dx equals secant squared x plus 2x plus 5 is a first order differential equation because there's only a first derivative. It's also known as an exact differential equation. That's more of a thing for probably calculus teachers than something that you need to be aware of. But that's because the derivative is all by itself, so you can just integrate both sides to get the solution, which you can see in the yellow is tangent x plus x squared plus 5x, and then you get that constant of integration. So with the plus c in there, the constant of integration, that's known as the general solution to the differential equation. So as you can see, because c can be different things, what you really get is a family of functions. And in this case, they are all vertical translations of each other. As you choose different values for c, you will just move that curve up and down so that it crosses the y-axis at a different place. To find a unique solution, as opposed to that infinite family of solutions that are given in the general solution, we need more information. So if the general solution is to a first order differential equation and it's continuous, then the value of the function at a single point, which is known as an initial condition, is all that we need. That solution, once we use the initial condition to determine what that value of c is referred to as a particular solution. The differential equation, together with the initial condition, is called an initial value problem, and that part is more of a calculus teacher thing. So, for example, if we have dy dx is equal to e to the x minus 6x squared, and we have the initial condition that it contains the point 1, 0, that's telling us a value of x that goes with a value of y. X is 1 when y is 0. Then we can solve that. I'm going to get rid of that stray mark. So what we can do then is we can solve that differential equation just by integrating both sides, and we'll get y equals e to the x minus, let's see, 1/3 x cubed times 6 will make that a minus 2x to the third, and we'll get a constant of integration. When we plug in the 1 for x and the 0 for y, we get 0 equals e minus, that's going to be 2 plus c. So that means c is going to be 2 minus e. So that then becomes our particular solution, that y is equal to e to the x minus 2x cubed, and we get that plus 2 minus e as our constant. So that's known then as the particular solution. Now, in the green here, we see if the general solution to the differential equation is discontinuous, then the initial condition is only good for a small piece of the curve, and the domain needs to be specified. So in the one we just did, this is continuous everywhere, so we don't have to worry about the domain at all. But in this next one, we can see that if we integrate both sides here, we're going to get y is equal to x squared, and then the integral of secant squared is a tangent, so that's going to be a minus tangent x plus c. The initial condition 0, 3 means that y is going to be 3. When we plug in 0 for x, we're going to get 0 squared is 0. The tangent of 0 is also 0, so that tells us that c is equal to 3. So we're going to get y is equal to x squared minus tangent x and then that plus 3. Because the x value was 0, and we know that a tangent of x has this, if you remember what the graph looks like, you're going to get vertical asymptotes at pi over 2 and negative pi over 2. So there are discontinuities at both negative pi over 2 and at pi over 2. So the continuous domain, that part of the domain that is continuous, that contains our x value, is only between negative pi over 2 and pi over 2. And so this solution would only be valid on that domain. If we wanted to know the value of the solution somewhere else, we'd have to get a different initial condition, one that had an x value on that particular domain, and then we would have to recompute what that value of c was. That's getting into the kind of more subtle parts of solving differential equations. So sometimes we can't find an antiderivative that is a solution to the differential equation, and that's known as a closed form solution. But we can still find the solution using the fundamental theorem of calculus. And this is something we talked about in the last chapter, that we can create a function that is defined as an integral. So if we want to solve the differential equation that the derivative is equal to e to the negative x squared, there is no closed form solution to the integral of e to the negative x squared. So instead, what we do is we just build a solution. We build a function that's defined as an integral. And you may remember we're going to go from some constant to x. We'll call the integrand e to the negative t squared dt. That builds something so that f prime of x is in fact equal to e to the negative x squared. To then satisfy the initial condition, we modify this further, and we choose that value of a to be the value of x that comes from the initial condition. So now we have built this so that its derivative still satisfies our differential equation. It's the e to the negative x squared that we want. At this moment, f of 7 would be the integral from 7 to 7, which would be 0. To make that be 3, we just add that in there, and this becomes our constructed solution to that differential equation with that initial condition. Okay, let's go on to the next panel. So let me slide this down a little bit. So, oops, didn't mean to make that stray mark there. Let me see if I can erase that without erasing everything else. Nope. Let me try that again. Let's see if that will do it. Nope. So I'm going to put that word the back in there. Okay, so what the idea for Euler's method is we're going to use this linearization to piece together little line segments to build a continuous approximation to the curve that is a solution to the initial value problem. So we're using the whole local linearity thing of a differentiable function. So here's our strategy. We're going to begin by finding an equation of a tangent line using the point that was given to us as the initial value. So there's our point. And then we'll use that value of x and y if we need it in the differential equation to then figure out what the slope is. Then once we know the slope and the point, we can get an equation of the tangent line. Then we use that tangent line, that equation of that tangent line, as a temporary function. We then plug in the starting value x plus whatever the delta x that's given to us, and we plug that into the tangent line to get a new value of y. So we have our new x plus delta x, y plus delta x that gives us our new ordered pair xy. Then we go back and repeat the process that we did by finding a new tangent line at that point xy, and we step that over and we kind of imagine that we're using this tangent line to kind of start at the initial point. We'll get a little tangent line segment and move to a new point. Then we'll recompute what the tangent line is at that point and use that tangent line as a little segment until we get a little further over. Then we'll get this point and get a new tangent line. And so we piece together this little kind of segmented solution curve using tangent lines for short little periods. So let's see what it looks like with an example. I'm going to try to slide this up. So here is our initial value problem. We have the differential equation dy dx is x plus y. We have the initial condition f of 2 equals 0. We're told that our delta x is 0.5, and we're going to approximate f of 3. So I'm going to start by finding a tangent line using our initial condition. So there's our point 2, 0. And then we're going to use this 2 and 0 into our differential equation to get the slope of the tangent line. So the slope of the tangent line is our derivative, and when we plug in 2 and 0, that's telling us that the slope of the tangent line is 2. So that means we have y minus 0 equals the slope 2 times x minus 2, or I'm going to go ahead and distribute that and say our tangent line is y equals 2x minus 4. Now, we're going to treat that like it's the function and step our x value over another 0.5. So we started with an x value of 2, so our new x value is going to be x plus delta x. That's the 2 plus 0.5, so that's going to be 2.5. We're going to plug that into our tangent line here to get a new value of y. So our new values of y is going to be 2 times the 2.5 minus 4. So that's going to be 5 minus 4, which is 1. So that's now creating a new point, 2.5, that's our x plus delta x, comma 1, that's our new y value that we got from the tangent line. Now we repeat the process all over again using now this as our ordered pair. So here's our new point, and now we're going to come back to our differential equation to get a new value of the slope and get a new tangent line. So the slope is again going to be our dy dx, but this time our x is 2.5 and the y is 1, which is going to make our slope be 3.5. We now take our new point and we're going to get our new tangent line, y minus 1 equals the new slope 3.5 times x minus the x-coordinate, which is our new x-coordinate of 2.5. So from here, let's see, we're going to get y equals 3.5x, and then the 3.5 times the 2.5. I'm going to grab my calculator here real quick. 3.5 times 2.5 is 8.75. So that's going to be a minus 8.75. And then we're going to add that 1 to the other side. So that means we're going to get y equals 3.5x minus 7.75. Now we're going to use this to get our next value. So we're going to get y equals 3.5. Now we're going to add a delta x, which is our 0.5, to our old x value. That's the 2.5. So that's now going to be 3. And then we're going to subtract the 7.75 from that to get our new value of y. So 3.5 times the 3 is going to be 10.5 minus the 7.75 is going to be 2.75. Now remember, this is the value we got at 3, so this is exactly our approximation to f of 3. It's going to be 2.75. Okay, let's try another one. I've got another example on the next panel. So we're going to repeat the process here. Now, typically on AP questions, you're never going to have to do more than 2 iterations of this. Our book and most books will create a kind of a way of doing this as a table of values. And that's nice, I think, if you're going to do like a whole bunch of approximations. And you may do some of those in your homework problems where it may ask you to do like 5 iterations on this, which gets a little bit cumbersome when you're making tangent lines each time. But I think this does a better job of kind of reinforcing where this is coming from and reinforcing the concept behind it rather than just making it a mechanical table of values. I graded a question like this on an AP exam years ago, and the people that did the way that I'm showing it here scored much better than the people that tried to do a table of values. They were really, I thought, kind of harsh and picky about making sure you labeled everything very specifically on the table, and so most people that tried to use the table didn't score very well on it. Okay, so here's our first tangent line. So we're going to come up with our tangent number 1 here. So we've got our point, which is 1, 1. This time we can see the delta x is a negative 0.5 because we're going to go backwards to the left and try to approximate f of 0. The slope is going to come from our differential equation. So if we plug in 1 for x and 1 for y, we're going to get 2 times 1 minus the 1 is going to be 1. So our slope is 1, our point is 1, 1. So we get y minus 1 is equal to the slope times x minus 1. And so that's going to be y equals x minus 1. And then we're going to add that 1 to the other side. So our tangent line is just y equals x. We're going to use that tangent line to get a new ordered pair. So we're going to plug in for the x, our previous x, plus the delta x. So that's going to be a 1, and then we're going to get a minus, plus the 0.5, or minus, plus the negative 0.5, or the minus 0.5 is going to be just a 0.5. That's going to make our new ordered pair, xy, is going to be our x plus delta x, so the 1 minus 0.5 is a 0.5, and our new y value is also a 0.5. So now we go to our differential equation so that we can get the slope for our second tangent line. So again, going 2x minus y is going to be 2 times the 0.5 and then minus the 0.5. And so that's going to look like 1 minus 0.5, which is 0.5. So there's our slope. So our tangent line, our second tangent line, is going to be y minus the y coordinate that's a lot of 0.5s. The slope times x minus the x coordinate. And so we can actually just go right from here. We're going to evaluate this at the next delta x over. So we were at 0.5. We're going to get y is equal to, I'm going to add that 0.5 over. We've got the 0.5 times, and our 0.5 minus 0.5 is going to be 0, minus that 0.5 that was part of our tangent line there. And so we're getting y equals 0.5 plus, and that's going to be a negative, I believe, 0.25, which is going to make our y value be 2.25. So our approximation to f of 0 is that it's going to be about 0.25 using Euler's method. Very good.